let's talk about geometric sequences. The definition reads, a sequence AN is a geometric sequence if it can be written in the form A times R squared, A times R to the n minus 1, for some non-zero constant R. The number R is called the common ratio. Each term in a geometric sequence can be obtained recursively from its preceding term by multiplying by R. So AN is equal to AN minus 1 times R for all n greater than or equal to 2. So this is one of the sequences that's defined recursively or has a recursive rule or definition. And what that means is that in order to find a term, I need to know the value of the term before it. So for instance, if I want to find the A4 term, I need to know the value of the A3 term. I multiply it by R, the common ratio, and I can find A4. Well, this is all fine and good, but sometimes I just want to know what the A8 term is. And I don't care what the A1 through A7 terms are. So is there a way that we could find an explicit rule for this kind of a sequence? Well, let's think about this A4 term that we have written up here. We know what A3 is, don't we? If we go back to this recursive definition over here, it says that A3 is going to be equal to A2 times R. Well, I could substitute in for that A3 term, and I'm going to have A4 is going to be equal to now A2 times R times R. But I also know what A2 is. Again, from that recursive definition, it's going to be the term before it, which is A1 times R. And again, I can substitute in for A2. So now I've got A4 is equal to A1 times R times R times R. And if we clean that up a little bit, we've got A1 times R cubed. Well, let's think about this for a minute. If I'm looking at the A4 term, that means that n is equal to 4. And that means that that 3 up there is equal to n minus 1. So now I can write a general expression for the anth term, which is going to be equal to A1 times R to the n minus 1. And as long as I know what the first term is, that A1, and as long as I know what the common ratio is, I can find any term that I want in that sequence without knowing all of the terms before it. So I'd like to look at a couple examples just to get us familiar with finding this explicit rule for a sequence. So the first sequence that I would like to look at has elements 2, 6, 18, 54, and 162. Now this is a finite sequence. There's no dot, dot, dot. It only has these 5 terms. And let's try to find an explicit rule for this sequence. Well, to do that, using my formula up here, I need to know A1 and I need to know R. So what is A1 equal to? Well, it's going to be the first term in my sequence, so it's going to be 2. Now we need to find the common ratio, R. Well, to do that, we really need to compare 2 terms, and so we might as well compare the first 2 terms here. And by using the recursive definition, we know that A2 is going to be equal to A1 times R, and A2 is that second term, which is 6. A1 is 2, like we just established, and then the only unknown that we have in this equation is R. So if I divide both sides by 2, then I get R is equal to 6 over 2, or R is equal to 3. And now I can write my general formula, my explicit rule here, which says that AN is equal to A1, which in this case is 2, times R to the n minus 1. And now I have an explicit rule for this sequence. All right, I would like to look at one more that's going to have a little bit something different in the elements of our sequence. So this sequence has elements 3, 1, 1/3, 1/9, 1/27, and 1/81. Now again, this is a finite sequence because there's no dot, dot, dot. It's just these 6 terms. And again, we'd like to see if we could come up with an explicit rule for the members of this sequence. So to do that, we need to know the first term and we need to know the R value, because remember that AN is equal to A1 times R to the n minus 1. And we need to find those two things. So looking at this sequence, what's A1 going to be equal to? Well, it's going to be equal to 3, that first term in our sequence. And what's R going to be equal to? You might be able to do this by inspection. You might be able to look at the progression of numbers in this sequence and figure out what it is, but it never hurts to check. So again, I'm going to take my first 2 terms. I'm going to remember from my recursive definition that the second term has to be equal to the first term times R, or that common ratio, and I'm going to substitute in. So A2 is equal to 1, A1 is equal to 3, and I have R. I'm going to divide both sides by 3 to get R by itself, and I'm going to end up with an R value of 1/3. So if I substitute back into my explicit rule up here, I'm going to have AN is going to be A1, which is 3, times the R value, which is 1/3, to the n minus 1. Now, that is an answer. And if you substituted in the various n values from 1 to 6, you would be able to generate all of the terms in the sequence. But I look at this and I say, well, I have a 3 times a 1/3 to a power. There has to be a way that I can simplify that. There just has to be. I have too many 3's in too many places, and I just need to be able to do that. So I'm going to try to simplify it. And I'm going to remember that the 1/3 to the n minus 1 is really 1/3 to the n minus 1. And then I'm going to remind myself that if I have an exponent in a denominator, I can make that exponent negative and move that to the numerator. So this is really going to be equal to 3 times 3 to the negative n minus 1. And I can do a little simplifying here. I've got still my 3 out in front, my A1 term, times 3 to the negative n plus 1. And now I've got like bases. I have 3 to the 1 here, and I have 3 to the negative n plus 1 here. And I can combine those bases. So now I can say that an is equal to 3 to the negative n plus 2. Now, whenever one does some funky algebra and some bizarre simplification, it's usually a good idea to substitute in and make sure that we can recover the first couple of terms of our sequence. So if we let n be equal to 1 up here, we're going to get 3 to the negative 1 plus 2, which is going to give us 3 to the 1, which is 3, and that is in fact the first element of our sequence. So far so good. So let's let n be equal to 2, and now I've got 3 to the negative 2, I'm just substituting in a 2 everywhere I see an n, plus 2, and that's going to give me 3 to the 0, and we know that any number raised to the 0 is equal to 1. Okay, that's the second term. Looking pretty good. Let's just try one more. So I'm going to look at n equals 3, So this is going to be 3 to the negative 3 plus 2, or 3 to the negative 1, which is in fact equal to 1/3, and that is the third element of our sequence. I'm not going to do any more. I think we've proven that our explicit rule does in fact generate the sequence in question. And in the next video, we're going to go and do exercise 17 from the book.